Hi everyone, welcome back to Bluware. My name is Julian Chenin and I'm a geophysical data scientist here at Bluware. We have a very exciting topic for you today. We'll be talking about deep learning, its uses across many different industries, but also how we're bringing that back to the subsurface. We've seen technologies such as AI really have a strong hold in sort of the car industry as well as the medical industry, and we're seeing that same kind of methodology being applied to the subsurface, helping us better characterize the Earth. So today we're joined by our lead data scientist for the R&D team, as well as our chief sommelier, Monsieur Benjamin Lartigue. So thank you for coming. Tell us a little bit about yourself, what are your experiences and your background.
Yeah, thank you, Julian. So basically I arrived like in 2016 in the US, and I did my double Master of Science and everything in France. And then since this day, I did like 6 years basically in the oil and gas and medical industry about deep learning and data science in general. So deep learning first is like a subset of what we call machine learning. There's a subset also of artificial intelligence.
Right.
And that's what you hear every day today. And these three combined are divided in two subsections. They are like basically supervised and unsupervised deep learning.
Gotcha. So really sort of the all-encompassing term is AI, but then you have ML and then you go a little deeper and it's now deep learning.
Basically, yes.
So you talked about supervised and unsupervised. What exactly is that? Could you help explain to our audience?
Yeah, no, for sure. Like the first concept you need to understand is what is like a label, basically. A label is like a tag or a name that you associate to like an image or something. So let's take a small example. If you want to identify like images of cats and dogs and say that this image is a cat or this image is a dog.
Right.
So basically the label is gonna be like the category, like this image is a cat. So let's say that this is a value 0, or this image is a dog and this is value 1. And so the association between like basically this label that you do on multiple like samples will create what you call like a label dataset. And that's why we call like basically supervised technique or supervised machine learning. And so now what is like unsupervised? Unsupervised is you don't use any labels basically. So what you need to do is to try to find in the data itself some pattern, some association directly without any labels.
I see.
So for example, you can have like some clustering when you're trying to cluster the different type of people for some marketing purposes or whatever.
Right.
And that's why we do like basically at Bluware, we do basically supervised and unsupervised, but most of the research is based on supervised deep learning or machine learning.
I see. Actually labeling the data is the majority of
yes,
what we
definitely.
do. Exactly. So I guess that's kind of the big buzz that we've been hearing about in the news, right? Deep learning and etc.
The funny part is like everyone is talking about like deep learning or artificial intelligence in the press, but the thing is, at the end, it's just math and algorithm. There is no like robot that's trying to invade us or whatever you see like in the movies. It's just like a lot of like products of matrices and a lot of like algorithm that we're trying to bring.
Exactly. So let's kind of strip away, sort of the black veil or the sort of black box about deep learning. Let's go deeper into deep learning. How does it work? How does deep learning work?
Yeah, so I think the most important thing you need to understand is we use what we call like something called like CNN, which is basically convolutional neural network, which is a stack of a lot of layers, a lot of like hidden layers. And basically the idea is you have like images of cat and dogs, and the goal is to say like I want to know if this image is a cat or a dog, basically.
Right.
So your input of your model is gonna be the images of the cat and the dog, okay? Your output is gonna be the categories, the labels that we talked about before.
Right.
So it's gonna be either that's a cat or either that's a dog, basically, okay? And so you train basically a model with the association of like this input and this output, like the combination of your features and labels. And when your deep learning is trained enough, you have like good metrics basically on it that tell you that this model is like perfectly trained. You can do what we call like prediction. So what is a prediction is you basically give now like that your model is good enough, like new images, so an images of a cat or a dog, and the system is gonna technically tell me directly if it's a cat or a dog. So that's basically what is deep learning in a nutshell.
Gotcha. Okay, so it's really not magic then. It's just sort of, it's math at the end of the day, correct?
Yeah. So the problem is like an optimization problem, basically. It's like a non-linear optimization problem. So what you want to do is you want to try to find like basically a solution for this problem. The problem is there is no way to find an exact solution. So we try to find like what we call an approximation.
I see.
Why we do that? Because these deep learning models are gigantic. It's millions and millions of parameters. So for example, for UNet, which is a special architecture of CNN, you have like roughly 16 million of parameters.
Only 16 million.
Yeah,
right?
and that's a small network. You can get like even bigger than that. So it can be huge. So you go like into like a multidimensional space basically.
I see.
To do that. And to train that, there is no way mathematically that you can find the exact solution. So you do like an approximation.
I see.
And basically what you do is you're trying to use an algorithm that is called gradient descent.
Okay.
And so why you want to do that? Basically, you have like what we call a cost function. There is like the loss function. There is definitely your goal of your problem is to find the minimum. And so the difference, this loss function is defined as the difference between the prediction and your labels. If this difference is like close to 0, that means the too much, that means your model is perfect, and then you're very happy.
I see. Yeah.
And so the idea is to like, whenever you have like this gradient descent, is to find like, to start with a random point and try to find like the bottom of it basically, yeah.
Right.
Like and that's what we call like the global minima. And this global minima, to find it, you start for this random point and you will try to find what is the deepest slope basically.
Right.
To go to find like the fastest possible this like global minima. Yeah, this descent. And so you can be stuck in some local minima, but the idea is to try to do everything that you can to touch the bottom of your curve.
Exactly, to escape that.
To find the minimum and then to find basically the best solution for your deep learning. And so that's what is deep learning in a nutshell on the mathematical part.
I see. Okay. And so those same concepts, right? We're using them for a myriad of different things, whether it be in the medical industry or in the car industry. We can still apply those same things to data, to seismic data, correct? Because instead of taking an image of a human's brain, now we can take images of the subsurface, right?
Exactly. So we apply this in seismic, but we can apply this also like with the self-car industry when you're trying to find like basically like automatically in real time to find the cars or the traffic lights or etc.
Right.
Also, for example, like for in the medical industry that you want to try to identify automatically where is the brain tumor in the MRI.
Right.
But today, like Julian is saying, like in Bluware we apply this basically in seismic. So how do we do that? The idea is come back to the same principle that we have with the cat and the dogs.
Right.
So a geophysicist is gonna come and try to tag basically, it's gonna try to tag like basically where is the salt on the seismic.
Right.
And that's gonna be what we call a binary segmentation.
I see.
Because you're trying to find the boundaries between like where's the salt and where's the non-salt. So to come back to our problem we talk about with the cats and dogs, basically. So in our case, for example, the salt is gonna be the 1, the value 1, and the non-salt is gonna be the value 0.
Exactly.
And you want to learn, compared to the cat and dogs, this time you want to learn that for each voxel, each pixel, to say that this pixel on my seismic is a salt, or this pixel on my seismic is a non-salt, basically.
Right.
And that's what you do, like a binary segmentation. And then the association, or like now the features, there's gonna be this time the images of the seismic compared to the images of cat and dogs. And the labels, there is like what I just said, that basically this is like a salt, this is a non-salt. You send that to the deep learning, you train on this, and that's how you create basically your deep learning model.
Right.
But the last thing that is different now from basically the cat and dog categories is now you train like these gigantic images of seismic.
Right.
And the problem is these images are way too big, so we need to like get some subset of these images, what we call like patches, that we set to the deep learning, and we train that will constitute basically your label set. And that's what we do to basically apply deep learning on seismic.
Right, because those seismic volumes, they can be as small as say a few miles, but really they can span thousands of miles, if not thousands of kilometers, right? And
exactly.
So we need to decimate that to feed it efficiently.
Yeah, and it's terabyte and terabyte of data when you think about it.
And that's on the light side too.
Yeah.
Definitely.
For sure, yeah.
And what's absolutely fantastic about this is that it really helps reveal those finer details, because now you can come through those massive data sets, right, at large, large and tease out those small subtleties within the data, understand what is the true distribution of my salt. But it goes further beyond that, right? That it's in any geological sense. It can be applied to faults, it can be applied to channels, really characterizing the full extent at a very high level of detail of the subsurface, which is fantastic. Building off of that, we talked about deep learning, how it works, what we need to do. So we talked about the present. What's the future? What's the path forward?
The future of deep learning is to understand like two concepts. The first concept is, I think, like the data pipeline. It's like the way that you feed the images, your features and labels to your deep learning. And that's the most important part, because if you don't feed like good example to the deep learning, your deep learning is not gonna get you like good results.
Exactly.
So that's, I think, the first one. How do you efficiently like give like a distribution of your positive labels, like the salt or the non-salt or the different categories, and to get basically as fast as you can the best model possible.
Right.
And the second option, I think, that is very important that we need to like get focused on, I think it's the architecture of the deep learning.
I see.
So we talk about, for example, UNet, there is like a special architecture. But basically it's like, how do you stack these different layers that what we saw on the example of the cat and dogs? And like in an efficient way, and also to not create like gigantic models, basically. And that's I think like the two first things is the architecture, the data pipeline. And thanks to today, basically, thanks to the advancement that we have on graphic cards, on the power of the graphic cards, we can finally compute these models. Like maybe 10 years before, we already know like basically what we can do with deep learning, but we didn't get basically the power that we can do today. So thanks to the NVIDIA graphic cards that we have, like, and everything related to that, like basically the tensor core that are inside that let us to like compute way faster everything, or the some equipment that we have like called like TensorRT that basically let us to try to do like the prediction as fast as possible. Thanks to that, we can create like deep learning model very fast and very efficient compared to like 10 years ago.
And we're seeing about this also recently in the news, right? Andrew Ng was talking about how we need to start thinking more critically of how to augment our data, really, and sort of maximize that to accelerate the way that we do things, but also get better models, better results. That's kind of the fundamental piece that we're kind of missing and where we're going in the future. And it kind of brings me to the, sort of this third point, right? There's this interactivity component, which we're having here at Bluware. Can you talk more about that?
Yeah, no, I think the interactivity is like something that a lot of people doesn't do so far, and that's how we differentiate for competitors as of today with Bluware. Basically, the interactivity is like you train like a model. There is like a smaller model, let's call it, compared to like this gigantic model that we have like ResNet or other model. And we develop basically this model at Bluware. They are like a little bit like smaller. And by doing this model smaller, you can get faster feedback, basically.
I see.
And so that's how we call it interactive, because instead of waiting hours and hours, like 3 hours, and then the data scientist is like, oh, like this parameter was bad at the end. We basically create this small model and you can have results in like 40 seconds. And then you can update the model on the fly and get better results at the end.
Exactly. Better results, but also working through it much faster, right? Because instead of waiting all these hours, now you can correct it in the process.
Exactly.
In real time.
Yeah. The biggest question as of today is like, where do we want to apply deep learning, and do we need to apply deep learning? I think that's the biggest question. And the third one is like, how do you apply it efficiently? Because there is maybe a lot of problems that you can apply and like solve this problem without deep learning, with like some simplest method. But like you don't need to apply deep learning all the time. And when you do, like you want to have like fast results and the best results, and how you do that. And I think that's what we need to teach people today, and like especially like the top level management or whatever, is like that you don't need to apply deep learning everywhere, but when you apply it, you need to do it correctly, basically.
There's a time and place, right? It's fit for purpose. It's not a one-size-fits-all solution. It's critical to effectively apply them to the proper problems, right? Exactly. Well, awesome. Well, thank you so much for sharing your perspectives, Ben, and your experiences, and also kind of your thoughts and sort of where deep learning will be going into the future. I certainly learned a lot. It's been a pleasure, and it's always great working with you because we still learn more as we continue progressing. So thank you again for stopping by, and
thank you, Julian.
Appreciate it.
Thank you so much.
Definitely. Thank you. Thanks for watching. If you learned something today, be sure to let us know in the comments. We'd love to hear from you.